Hi everyone, in this video we're going to be looking at section 11.5, which is lines and planes in space. Lines in space is subsection 1. In the plane, slope is used to determine the equation of a line. In space, it's more convenient to use vectors to determine the equation of a line. So remember when you are in two dimensions and you're trying to find the slope of a line, you either need a point and a slope or you need the slope and a y-intercept. Right? Well, that starts to get a little bit vague because remember in the three dimensions, I need three dimensions, right, for a slope. And the slope is only defined the way we know it as rise over 1 or y over x, and that doesn't account for z. So a vector is kind of like a slope because it takes all three coordinates into effect. So let's consider the line L passing through the point P, which is x sub 1, x sub y sub 1, and z sub 1, and parallel to the vector V, which is ABC. So in our picture here, this is our vector V sticking out from the origin, and this is my point P, right? And so the vector V is what we're going to call the direction vector for the line L. So if you see in this case, the line L is just the line from P to Q. And A, B, and C, which are the coordinates of the vector, are called the direction numbers. So one way of describing the line L, which again here the line from P to Q, is to say that it consists of all points Q for which the vector PQ is parallel to V. So in the picture here, this value, this point Q, and if I take this point from P to Q, that vector is parallel to V. So that point is on the line, right? If, for example, I took Q to be over here, right, then I would have, this would be the line from P to Q, and this would also be parallel to V, and so that is a Q that we include in that line, right? So again, the line L that is bold-faced here is going to be described as all points Q for which the vector Q is parallel to V. So every single point that when I connect it with P, I get a line parallel to, or a vector parallel to V. This means that PQ is a scalar multiple of V. Remember, that's what it means to be parallel, is to be a scalar multiple. So in other words, I can write PQ is equal to some constant T times V, because PQ and V are parallel. So we have PQ. Well, PQ is a vector, and how do we find that? Well, we take the terminal points Q minus the initial points P, right? So x minus x1, y minus y1, z minus z1, right? And that's how we could describe PQ. But then by this equation here, we know that's equal to TV. Well, what is TV? Well, TV is T times V, which is this vector here. So it's TA, AT, BT, and CT. And so we end up getting this equation, right, do it in orange, or we'll do it in red here, this equation right here that is equating two vectors, right? And so if we equate the components, then we obtain parametric equations of the line in space, or of a line in space. So that's the idea for theorem 11.11, parametric equations of a line in space. A line L parallel to the vector V and passing through the point P, which is x1, y1, z1, is represented by the parametric equations. Here we get three of them because there are three coordinates. We get x sub 1 plus at is x, y is equal to y sub 1 plus bt, and z is equal to z sub 1 plus ct. So one thing to notice here is, remember in the two dimensions, what two things do we need? Two of three things do we need in order to write the equation of a line? We either need a point in the slope or the y-intercept in a slope. Here, in order to write the equation of a line in space through parametric equations, we need to have a vector and a point. So those are the two things that we need in order to write the equation of a line in space. So if the direction numbers A, B, and C, remember those are the coordinates of our vector, If those are all non-zero, then we can eliminate the parameter t. In other words, solve each one of these for t and plug it into the other, and we'll obtain what are called symmetric equations of the line, which are these. It's just x minus x1 over a, which is equal to y over y1 minus a, which is equal to z minus z1 over c. I think I said a, but I meant to say b there. But the idea is if I solve each one of these for t, then I can set them equal to each other, and I get those symmetric equations. Okay, so let's go ahead and do this. Find the parametric and symmetric equations for the line L that passes through the point 1, negative 2, 4, and is parallel to V. So we have our point, and we have our vector, right? It's not our slope, it's our vector. So now it's just a matter of plugging it into these equations. So just since this is the first time we're doing it, x sub 1 is going to be 1 because it's the first component of our point. Y sub 1 is going to be negative 2, and z sub 1 is going to be 4. And then my direction, what do we call those? We call those our direction numbers, are A, B, and C, and those are the components of my vector. So 2, 4, and, whoops, 2A is 2, B is 4, and C is negative 4. And so in order to find our parametric equations, we just plug in those values, right? So x is equal to x sub 1, which is 1, plus a times t, so plus 2t. So that's my x parametric equation. Y is equal to negative 2 plus 4t, and z is equal to 4 minus 4t. And it's really just that easy. And now, since all of my direction numbers are non-zero, we can get our symmetric equations, which again is just this formula here. So I get x minus 1 over a, which is 2, x minus negative 2, so plus, sorry, I should say y, right? Y plus 2 over top of 4, and then z minus 4 over top of negative 4. So those are my symmetric equations. Neither parametric equations nor symmetric equations of the given line are unique. So remember when we talked about parametric equations to begin with, parametric equations are not unique, right? Depending on what our parameter is, if we say our x is equal to t plus 1, then that gave us a set of equations for x and y, and if we said x was equal to t minus 1, that gave us another set of equations. Same thing goes here. Parametric equations are not unique. Okay, so we want to find the parametric equation of the line that passes through these 2 points. So remember, what do we need to write the equation of a line in space? We need a point and we need a vector. In this case, we're given 2 points but no vector. However, we can find the direction vector by just finding the vector that connects these 2 points. Right? So first we need to find the direction vector. And again, that's just going to be the vector that connects these 2 points. So that's going to be, we'll call it V, but really that's just this vector that connects P and Q. If we call this one P and we call this one Q. So again, it's just initial minus terminal. So in this case, it's 1 minus negative 2. So 1 plus 2, 3 minus 1, and 5 minus 0. So this is 3, 2, and 5. And so this is my ABC. And then I can choose any point. So we'll take the point. Let's just say the first point here, negative 2, 1, 0. And so I get x is equal to negative 2 plus 3t. Y is equal to 1 plus 2t. And z is equal to 5t. Right? And that is a set of parametric equations for the line. Okay, so now let's talk about planes in space. In space, we can obtain the equation of a plane from a point on the plane and a vector normal, i.e. perpendicular to the plane. So consider the plane containing the point P, which is x1, y1, z1, and having a non-zero normal vector n, which is given by ABC. So remember, a normal vector, again, it's this vector that comes out from the plane at a right angle. Right? So the plane consists of all points. This time, all these points Q, like say a Q over here and a Q over here, as long as the vector PQ, so the line connecting P to Q, is still normal or orthogonal to N. All right, so that's a way we can describe a plane in space. So remember, what does it mean for a, one way to tell if two vectors are normal is that their dot product is 0. So the claim is that Q, the plane is if I take any of these points Q, right, Q here, or even the Q that's written by the book here, and that vector is orthogonal to this normal vector, or I'm sorry, that is normal to this normal vector N. So in other words, the vector PQ is dot product with N is going to be equal to 0, right? So that is what it means to be on the plane, right? For Q to be on the plane, that means that the dot product of PQ with N is 0. Well, what is N? N we just defined as A, B, and C, that vector. And then PQ, remember, we know what P is. So in order to find PQ, if Q is X, Y, Z, it's just going to be terminal minus initial. So that's where we get this line here. It's just going to be N, which we know is A, B, C, and then PQ, which is terminal minus initial. And then if we do dot product, remember, what does it mean to dot product? That means first component with first component, plus second component with second component, plus third component with third component. And we get this equation here. So this third equation of the plane is said to be in standard form. Okay, so theorem 11.2, standard equation of a plane in space. The plane containing the point x1, y1, z1 and having a normal vector n equals to ABC can be represented by the standard equation of a plane, which is this equation here, exactly the same as the one I started above. So in other words, what we need in order to write the equation of a plane is we need a point and normal vector. Right? So for the equation of a line, we just need a point and a vector, right? And now for a plane, we need a point and a normal vector. And then if we were to go ahead and distribute the A, distribute the B, distribute the C, combine all of our like terms, we would get AX plus BY plus CZ plus some constant D, which would be A minus AX1 minus BY1 minus Z1C. Then setting it equal to 0, that is what's called general form. So not unlike how the general form of equation of a line has constants with X, Y, and Z, that's kind of similar here. And one thing that's convenient is if you have a general form of the equation of a line, right? If I have something that looks like this, then I can very easily see what the normal vector is, right? The normal vector is just going to be A is my X component, B is my Y component, and C is my Z component. So in other words, the coefficient of X, Y, and Z are just going to be the components of the normal vector, right? So for example here, example 3, the normal vector to the plane, negative 5x plus 7y plus 2z plus 12, that's a plane. And if I wanted to find the normal vector would just be the coefficient of x, which is negative 5, the coefficient of z or y, which is 7, and the coefficient of z, which is 2. All right, so that is the normal vector to the plane. All right, so now let's look at a little more interesting example. Let's find the equation of a line in standard form and general form of the plane containing the points A, B, and C. So in order to write the equation of a line, remember we need two things. We need a point and we need a normal vector. In this case, we're given 3 points but no normal vector. So to find our normal vector, remember what we can do is if we have two different vectors that have their tails meeting together, if we take their cross product, that will give us a vector that is orthogonal to both vectors, right? So in other words, if I take two of these, if I create two vectors from these 3 points, which as you can see in the drawing, that's what they do, then I can take the cross product of those vectors and that will give me my normal vector. So in other words, to find our normal vector, we must find the cross product. In this case, if I look at these equations, if this is my 2, 1, 1, we'll call that our A, right? 1, 4, 1 is here. This is our B. And negative 2, 0, 4, that's our C. So in other words, if I take the cross product of this vector with this vector, then I will find that will give me a normal vector. So what is this vector? This is the vector AC, and this is the vector AB, right? So what I need to do here is find the cross product of the vector AB with the vector AC. And if I do that, I will get my normal vector. Okay, so let's find, in order to find the cross product of those vectors, we have to first find the vector, right? So AB, again, how do we find this vector? It's just terminal minus initial. So this would be 1 minus 2, 4 minus 1, and 1 minus 1. So this would be the vector negative 1, 3, 0. And then if I took the vector AC, well, terminal minus initial is going to give me negative 2, minus 2, 0 minus 1, and 4 minus 1, which is going to give me negative 4, negative 1, 3. So those are my two vectors that I created from these 3 points, and now I'm going to take their cross product to get that vector that looks maybe something, if I tried to draw it here, maybe like this, and it points straight out from these two guys at a right angle, right? So that's kind of the idea here. So I'm going to take AB cross with AC, and remember, how do we do this? We do I, J, K. Components of AB are negative 1, 3, and 0. And the components of the other one are negative 4, negative 1, 3. So then I end up getting 3, 0, negative 1, 3, I minus negative 1, 0, negative 4, 3, J plus negative 1, 3, negative 4, 3, K. And simplifying this out, this gives me, I guess I'll put it over here, 9 minus 0, I, minus negative 3 minus 0, J, plus negative 3, and then I've got minus negative, so plus 12, K, which gives me 9I plus 3J plus 9K, which is not what I wanted. Let's see if we made a mistake here. Negative 4, 0, 3. I apologize for this. This one's 9 is fine. 3 is fine. So this would be negative 3 minus. Oh, that should be a. This should be a 1 here, right? So now I get, or negative 1, right? So this should be positive 1 plus 12, which gives me 13, which is what I wanted. Sorry about that. So, and then I'm just going to rewrite this as 9, 3, 13. So this is my vector, right? So this is my vector, my normal vector that has A, B. These are my A, B, and C coordinates, right? And remember my point, we could choose any of these 3 points. So for my point, let's go ahead and we'll just choose the first one, because maybe that's easier to pick, right? So this is my vector, this is my point. So now I write the equation of a line in standard form. Or not line, equation of a plane. So the equation of plane, remember, that's A times x minus x1. So A is going to be 9, and then it's x minus the x value of my point, which is 2, plus 3, and then y minus the y value of my point, so y minus 1, plus 13, and then it's z minus the z value of my point, which is 1, and it's equal to 0. So that is my standard form. Remember, to find general form, I just multiply everything out. So if I did that to find general form, I would get 9x minus 18 plus 3y minus 3 plus 13z minus 13 equals to 0. So I get 9x plus 3y plus 13z. And if I combined all those coefficients, I would get a minus 34 equals to 0. And this would be the equation of my plane in standard form. And as you notice, the coefficients of x, y, and z are exactly the components of my normal vector. Okay, so sketching planes in space. If a plane in space intersects one of the coordinate planes, then the line of intersection is called the trace of the given plane in the coordinate plane. So if you have a plane, anytime a plane intersects a plane, think about two sheets of paper intersecting with each other. They intersect at a line, right? And so when you take the one of the coordinate planes, right? So if I take like the YZ plane, the XY plane, or the XZ plane, and intersect it with the plane that we are concerned about, then that line is called the trace, right? So to sketch a plane in space, it's helpful to find points of intersection with the coordinate axes. In other words, find the x-axis, the y-axis, and the intercepts, right? The x-intercepts, the y-intercepts, and the z-intercepts. And that's just like finding the x and y-intercepts in the two-dimension, right? How do we find the y-intercept? We set x equal to 0. How do we find the x-intercept? We set the y equal to 0. Now that we have three things, in order to find the x-intercept, you set y and z equal to 0. In order to find the y-intercept, you set x and z equal to 0, and so forth. So what we're going to do here is we have this equation of a plane, and we want to sketch it. So what we want to do is find all of the traces, and then find all of the intercepts, and that will help us give a rough sketch of what we're going on. So first, let's look at the XY trace. So remember, the XY trace, what's missing? Z, right? So that's where z equals to 0. So if z equals to 0 in this equation, then I would be left with 3x plus 2y equals to 12, right? And we're comfortable with the x and y coordinate plane, so you know this is the equation of a line, right? I'd have to, I could solve for y and get y equals mx plus b, and that would be the equation of a line, which again is what we expect, right? This is intersecting the plane we're concerned about with the xy plane. So now let's do it with the, let's do the YZ trace. So again, in order to do the YZ trace, I set x equal to 0. So if I set x equals 0, I get 2y plus 4z equals to 12. We're not typically comfortable here with y and z as my variables, but it's just the same as in the case with the xy coordinate plane, right? There's no reason why we called the xy coordinate plane x and y, right? It could have easily been p and q, right? We chose those variables at random. So this is just another equation of a line. And then how about the xz trace? So again, this is going to be the equation of a line, and this is where y equals to 0. So this would look like 3x plus 4z equals to 12. So those are my three traces. So now let's find our intercepts. So let's find our x-intercept, right? In order to find our x-intercept, remember, what do? We set y equal to 0 and not x equal to 0 and z equal to 0, right? If I took my equation here and I set y equals to 0 and z equals to 0, then I would get 3x, y0, z0 equals to 12, and I'd solve that and get x equals to 4, right? So my x-intercept is 4, and then we plugged in y equals 0 and z equals 0. So now my y-intercept, again, how do we do that? We set x equals to 0, and z equals to 0. So if I do that, I would end up with 2y is equal to 12, so I get y is equal to 6. So I get 0, 6, 0. And then finally, let's see if I can scooch this up a little bit. Finally, if I get my z-intercept, again, I set x equal to 0 and y equal to 0. Then I would get, in that case, 4z equals to 12, which means z equals to 3, right? So that is 0, 0, 3. Now that we have intercepts and we know that since this is an equation of a plane and the planes are going to intersect our coordinate planes, x, y, y, z, and x, z in lines, we can kind of make a good sketch of this. All right, so this is my x, y, z. So this is x, this is y, this is z. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And now let's plot all these points. All right, so my x-intercept is at 4, 0, 0, which is right there, right? That's the point 4, 0, 0. My y-intercept is the point 0, 6, 0, 0. So 1, 2, 3, 4, 5, 6. So that's this point right here, which is 0, 6, 0. Let's scooch this one over a little bit. Try it again. And then my z-intercept is 0, 0, 3. So that's this point right here. Oops. And now if I connect, again, I know that these are going to connect at straight lines because these are going to be the equations of those lines that are the traces, right? The equation of these lines that I'm drawing is actually the traces. And then if you think about this, if I were to color in, think about this is a flat surface that I'm coloring in, then you can kind of get the idea of what this plane looks like, right? And it would actually extend forever this way and forever this way, but this plotting the x and y and z intercepts gives us a nice idea of what's going on. So if you do GeoGebra at all, this is an app, and I just plugged in my equation down there at the bottom, 3x plus 2y plus 4z equals 12, and as you can see, the red axis is the x-axis, the green axis is the y-axis, and the blue axis is the z-axis. And this is what the plane would look like if I continued it as a straight flat piece, right? We only drew the little section of it, but that's what the plane would look like. Okay, and a couple little things here. If an equation has a missing variable, such as the equation 2x plus z equals to 1, then the plane must be parallel to the axis represented by the missing variable. So that one is drawn right here. So if I look at the y variable is missing, so that's the y-axis, and I know that that plane is parallel to that axis, right? In other words, it doesn't cross it, right? And if two variables are missing, so it looks like ax plus d or something like az plus d or something like that, then it's parallel to the coordinate plane represented by the missing variables, right? So that's this picture here. All right, that's all I have for this video. Thank you.